Welcome everybody once again. So this is our 11th class for module 3. We have already studied about Bernoulli's equation and the applications of Bernoulli's equations for the cases of Venturi meter, pitot tube, orifice meter and orifices. So this is our next concept in module 3. So here we are going to study the flow through pipes. So when a fluid is flowing through pipes, the flow can be laminar flow or turbulent flow. Okay, when it is flowing through pipes, your flow can be laminar flow or the flow can be turbulent flow. And we know a flow is said to be laminar if the Reynolds number is less than 2000, and the flow is said to be turbulent if the Reynolds number is greater than 4000. And when the Reynolds number lies between 2000 and 4000, the flow is neither laminar or turbulent. That means it is in a transition state from laminar to turbulent flow. Now, see, we are going to study flow through pipes. And when a liquid is flowing through pipe, the liquid can flow through pipes fully or it can be half full. Okay, this is called half full. There is a gap in between the surface and the free surface of water. Here there is no gap. This is called the fluid flowing full. Here the fluid is flowing half full. So what happens is when the fluid is flowing half full. So this is an example in the case of sewer lines. So here they are partially full, half full or partially full. In such cases, the pressure inside the pipe will be same and this will be equal to the atmospheric pressure. That means the flow of a fluid, the flowing of a fluid in the pipe is not under pressure because it will maintain the atmospheric pressure. So the flow is not under pressure. But in this case, if the flow of a fluid is flowing full, then the flow of fluids through pipes will undergo some pressure. That means the flow of fluid through pipes is under pressure. So for this case, the flow is under pressure. So there will be pressure when the fluid is flowing full. So when we are studying flow through pipes, we will study this case. That is the first case. Flowing full. Okay, that is the flow is under pressure. Flowing under pressure. So that is the case for flow through pipes. And this case, not under pressure, that means atmospheric pressure is maintained, will be taken as an example for open channel flow, which we will study in the next module. So now we are studying flow through pipes. Okay, now while studying, so with this basics, we will move on to the loss of energy in pipes. So now I hope you understood what is the flow through pipes. So now we are going to study the loss of energy in pipes. Okay. So the loss of energy in pipes, as I have told you earlier, the pipes are running full, so it is under pressure. Now, when a fluid is flowing through a pipe, the fluid experiences some resistance due to which some of the energy of the fluid is lost. And this loss of energy are called energy losses. And these energy losses can be classified as major energy losses and minor energy losses. Okay, so the energy losses can be, so I told you why this energy, what is energy losses? Because when the fluid is flowing through the pipe, it experiences, that is the fluid experiences some resistance. Okay, and this resistance results in the loss of energy called energy losses in pipes. And these energy losses can be major energy losses and minor energy losses. So energy losses can be major energy losses and minor energy losses. Minor energy losses are negligible or very small when compared to the major energy losses. Now, this major energy losses is due to the friction. Okay, this major energy losses is due to friction. And this major energy losses can be calculated by using two formula. So the first formula for calculating the major energy losses is called Darcy-Weisbach formula. We call this as Darcy-Weisbach formula. Okay, so what is Darcy-Weisbach formula? That is the loss of head or energy. Energy losses means loss of energy head, right? So the loss of energy in pipes due to friction is calculated using the Darcy-Weisbach equation. And this Darcy-Weisbach equation is HF is equal to, that is the loss of head. H means head. Energy head lost due to friction. F means friction. Okay. Energy lost due to friction or loss of head due to friction is equal to 4FLV square by 2GD, where HF is the loss of head due to friction. We know the three heads are pressure head, velocity head and datum head. Okay, see in the Bernoulli's equation, we used to write P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So this is loss. Okay. So this loss can be major losses, minor losses or a combination of major and minor losses. So in order to determine this loss, we have different formula. So first formula to determine the major energy loss is Darcy-Weisbach formula. So HF is equal to 4FL square by 2GD, where HF is the loss of head due to friction. Now F, we have a term F here, right? This F is called coefficient of friction. This is called coefficient of friction. And this coefficient of friction, it depends on Reynolds number, or it is a function of Reynolds number. And this coefficient of friction is equal to 16 by RE. See, you should remember all these things. This formula, this coefficient of friction in order to solve the problems. 16 by RE, or that means 16 by Reynolds number if the Reynolds number is less than 2000. That means for viscous flow. Okay. Reynolds number less than 2000 means that is the case of viscous flow. If the flow is viscous, the coefficient of friction is equal to 16 by RE. And the coefficient of friction is equal to 0.079 by Reynolds number raised to 1 by 4 for Reynolds number is greater than 4000. So actually this case is Reynolds number from 4000 to 10 to the power of 6. In general, when it is greater than 4000 or turbulent flow. For the case of turbulent flow, Coefficient of friction is taken as 0.079 divided by Reynolds number raised to 1 by 4. Now we have a term L. So this L is the length of the pipe. So L is equal to the length of pipe. Now we have V, capital V is the mean velocity of a flow. So V is the mean velocity. V is the mean velocity of a flow. G is the acceleration due to gravity and D is the diameter of pipe. Okay. So very important, the Darcy-Weisbach formula and how to determine the coefficient of friction based on whether the flow is viscous or turbulent. Now we have one more formula to determine the major energy losses, that is energy losses due to friction, and that second formula is called Chassis formula. Okay, so second formula to determine the major energy losses is Chassis formula. So now Chassis formula is HF is equal to, HF means loss of head due to friction. That is why we are giving F. Loss of head due to friction means that is major losses. So HF is equal to F dash by rho G multiplied by P by A multiplied by L V square. See, this L V square is common, right? L V square. The other terms are F dash by rho G into P by A. Now, in this formula, HF is the same. So, HF is the loss of head due to friction. Now, this P by A, you can write this P by A as 1 by M. We will write or A by P. So, A by P is called, here A is called the area of cross section of the pipe. Okay. Area of cross section of pipe or the area of flow of a pipe divided by P is called the wetted perimeter of pipe. So A by P is area of cross section of pipe or wetted perimeter of the pipe, that is area by wetted perimeter, and this is called hydraulic mean depth. This A by P is called hydraulic mean depth and it is represented by the symbol M. So M is equal to A by P, area by wetted perimeter. Now what is area? Area is pi d square by 4 divided by wetted perimeter is pi d. Why the wetted perimeter is pi d? We know perimeter of a circular section is pi d. And why wetted perimeter is pi d? Because our assumption, our condition is when the flow through pipes is full under pressure. So the perimeter is pi d. So we get M is equal to D by 4 for circular cross section. So A by P is over. L is the same. L is the length of the pipe. So L is the same as the length of pipe. And V is also same, the mean velocity of a flow. Now we have F dash by rho G, right? F dash by rho G. So we will write this HF, we know. HF is equal to F dash by rho G into 1 by M into L V square. So from this we get V square is equal to rho G by F dash into M into HF by L. Now this HF by L is taken as I. What is HF? Head of loss due to the friction, and L is the length of the pipe. HF by L is taken as I, that is nothing but the loss of head per unit length of the pipe. Okay, so I is equal to HF by L, that is nothing but the loss of head per unit length of pipe. So we write this as I, nothing but the slope. So substituting the values, we get V is equal to square root of rho G by F dash M into I. Now we will consider this square root of rho G by F dash as C. So it is a C into root of Mi, where C is equal to square root of rho G by F dash. Okay, and this C is called Chassis constant. C is called Chassis constant. So the Chassis formula is velocity of a flow is equal to C into root of Mi. Okay, so you have two formula for determining the loss of energy for major energy losses. One is Darcy-Weisbach formula and the second one is Chassis formula. Here also Cf dash is called coefficient of friction. Here F dash is coefficient of friction, and since we are calculating this F dash in terms of Chassis constant, we are not determining its value. In the previous case, for Darcy-Weisbach formula, this coefficient of friction is determined in terms of Reynolds number. Here we are determining F dash in terms of Chassis formula. Okay, this F dash is expressed in terms of Chassis constant C. So velocity V will be equal to C into root of Mi. This is known as Chassis formula. Okay, so from V, from V using Chassis formula, we can determine the energy losses. Now we will move on to the second type of losses, that is minor energy losses. So minor energy losses are due to various reasons. Okay, so the minor energy losses is due to, first reason is due to sudden expansion of pipe. So we know sometimes the cross section of the pipe will be suddenly expanded. So due to sudden expansion of pipe. Second reason is due to sudden contraction of pipe. Now third reason is due to bend in pipe. Fourth reason is due to miscellaneous factors. Example is pipe fittings, etc. And the last reason may be due to some obstructions in pipe. So for each case, see, these are the different cases or different causes for minor energy losses. And for each cause, we have separate formula. So first cause for the minor energy losses is due to sudden expansion of pipe. So we have expressions, we have derivations for each minor losses by the application of Bernoulli's equation. So here we are not going to derive all the formula, we are just understanding the formula. Okay, so what is the loss of head due to sudden enlargement? So by considering the sudden enlargement, see if the pipe is suddenly enlarged, what happens? The velocity gets changed, the cross section gets changed. So we will apply the Bernoulli's equation, we will apply the continuity equation. So applying all these, we get the minor energy losses due to the sudden expansion of pipe as HE is equal to, E means expansion, okay, H means head lost or energy lost, is equal to V1 minus V2 the whole square divided by 2G. So G is acceleration due to gravity. See, when sudden expansion of pipe means it will be like this, right? So you can take section 1 here, you can take section 2 here. So V1 will be velocity of a flow at section 1, and V2 will be velocity of a flow at section 2. So since you are taking the square, you get V1 minus V2 square by 2G. I think you remember our formula is P1, formula for Bernoulli's equation is P1 by rho G plus V square by 2G, right? V square by 2G. See, this is the velocity head. So this equation is based on this. V is replaced by V1 minus V2 the whole square by 2G. This is the expression for minor energy loss due to sudden expansion of pipe. Now, our second cause is due to the sudden contraction of pipe. Sudden contraction of pipe means the case is like this. Okay. So the loss of head due to sudden contraction of pipe, the formula is HC is equal to, C means contraction, H means head lost. So HC is equal to 0.5, that is half of V2 square by 2G, where V1 is the velocity of a flow at section 1 and V2 is the velocity of a flow at section 2. So due to the contraction, the losses depends only on V2. It do not depend on V1 because here the cross section is larger cross section. So the contraction, the head loss due to contraction of pipe, it depends only on V2. Okay. So it is V square by 2G. It is replaced by V2 and half of this. Now, I told you the third case is it may be due to the bend in a pipe. That means bend in a pipe can be at the entrance of a pipe or in the exit of the pipe. Okay. So the bend can be in the entrance of the pipe or it can be in the exit of the pipe. So if the bend is in the entrance of the pipe, the formula is HI is equal to 0.5 V square by 2G. And if it is in the exit of the pipe, the formula is HO. That means outlet, input, inlet and outlet. Entrance is inlet, O, that is outlet. HO is equal to V square by 2G. Okay. So due to pipe fittings, you can take it as V square by 2G. No special formula is given for pipe fittings. And the last case is due to the obstruction in a pipe. So due to the obstruction in a pipe, the head loss. Okay, now see for the pipe fittings, you can take it as HB is equal to V square by 2G with some constants or coefficients. So K is the coefficients of pipe fitting. And generally, see if it is entrance and exit, you can use HI is equal to 0.5 V square by 2G and HO is equal to V square by 2G. And in between anywhere in the pipe, you can use HB is equal to K into V square by 2G, where K will be the coefficient of bend. Okay. Now, due to the obstruction in pipe. So head loss due to obstruction in pipe is given as H obstructions is equal to V square by 2G into, now we have to write a coefficient, right? So that is expressed as A by CC into A minus 1 the whole square. Where V is the mean velocity of a flow, G is acceleration due to gravity, A is the area of pipe, small a is the maximum area of obstruction. And Cc is the coefficient of contraction. And this Cc, coefficient of contraction, will be equal to area of vena contracta divided by A minus E. That is area of the pipe minus area of obstruction. So you get area of vena contracta is taken as AC divided by A minus E. Okay, so that is all about the losses in pipes. Now we have to solve some problems related to losses in pipes. So before solving the problems, we will see the next concept also. So we will see a few concepts first and then we will move on to our problems. So we saw the flow in pipes. And what about the losses? Major losses and minor losses in pipes. The next concept is hydraulic gradient line and total energy line. Hydraulic gradient line and total energy line. Very important concept. You can expect problems and some 5-mark question related to this hydraulic gradient line and total energy lines. Okay, and this is very important for you to study the flow of a fluid through pipes. Now, what is hydraulic gradient line? First of all, we will see what is hydraulic gradient line. It is expressed as HGL, hydraulic gradient line. And it is defined as a line which gives the sum of the pressure head and datum head. So we know the pressure head is P by rho G and the datum head is Z. So it is nothing but P by rho G can be expressed as WO, right? Rho is density, G is acceleration due to gravity. So it is weight density, WO plus Z. So this is called hydraulic gradient line. And this is with respect to some reference line. Okay. And it is also expressed as the line which is obtained by joining the top of all vertical ordinates showing the pressure head of the flowing fluid in a pipe from the center of the pipe. So how can you draw a hydraulic gradient line? So I will explain you what is the total energy line also. After that we will draw the diagram. So total energy line is defined as the line which gives the sum of pressure head, datum head and kinetic head. That means the velocity head of a flowing fluid in a pipe with respect to any reference line. So what is your pressure head? P by rho G plus datum head is Z plus kinetic head is V square by 2G. You can also express it as P by W plus Z plus V square by 2G. This is called, so the line joining these head, the summation of these head is called total energy line. So the line is called total energy line. Now, suppose you have a pipe, you have a tank and the water is flowing through the pipe. Okay, you have a tank like this, or you have a storing object and you have a pipe. Now, this is the center line of the pipe. So, this will be taken as the datum head. Okay, this can be taken as the datum head, and here you have the free surface of water. So now we have two types of lines, that is hydraulic gradient line and total energy line. Hydraulic, so this is our datum head, right? So this hydraulic gradient line is the summation of pressure head and datum head. So datum head is not changing. So this is our datum. But from this point to this point, the pressure head is varying. See, the pressure varies as it flows through a pipe. So, if you take this G as the hydraulic gradient line, you can take this point as C. So, this line will be called as hydraulic gradient line. See, everywhere the pressure head is varying, and when it comes to C, the pressure head becomes 0. Maximum it is here, okay? At this place, at point B, your pressure head is maximum, and at C, you will have minimum pressure head, it comes to 0. Now, what is total energy line? It is the line joining the pressure head plus datum head plus kinetic head. So, it will be the summation of kinetic head, okay? So, hydraulic gradient line. So, total energy line will be equal to hydraulic gradient line plus kinetic head. So, if you take this as E, that is total energy line E, okay. So, the velocity head is not changing from one point to another point throughout the pipe. Only the pressure varies. So, what happens is, this line is called total energy line. Okay, the difference between the HGL and total energy line is the kinetic head. So that is the concept behind hydraulic gradient line and total energy line. And before completing your module 3, you have one more concept in module 3, that is called equivalent pipes. Flow through pipes in series and parallel pipes. So we will see that also. After that, from the next class, we will move on to the problems related to these concepts. So next concept is, so far we have studied the losses, next about the hydraulic gradient line and the total energy line, and now we are going to see flow through pipes in series. Okay. That is pipes connected in series. See, you know, this is called series, right? And this is parallel. So this means parallel. So now, see, suppose you have a water body here and another tank or something is placed like this, and you have pipes. This is many pipes are connected in order to carry the water. Okay, so we have pipe 1, 2, 3, 4, 5. 5 different types of pipes. So you can take L1 be the length of pipe 1, D1 be the diameter of pipe 1, L2 and D2 be the length and diameter of pipe 2, L3 and D3 be the diameter and length of pipe 3, L4 and D4 be the length and diameter of pipe 4, L5 and D5 be the length and diameter of pipe 5. And see, V1, V2, V3, V4, V5 be the mean velocities of flow, mean velocity of a flow through pipes 1, 2, 3, 4 and 5. So we have defined L1, L2, L3, L4 and L5, D1, D2, D3, D4 and D5. Okay, so these are the diameters of the pipes 1, 2, 3, 4, 5. L1, L2, L3, L4, L5 are the length of the pipes L1, 2, 3, 4, 5. V1, V2, V3, V4, V5, etc. are the velocity of flow through the pipes 1, 2, 3, 4 and 5. Now, let F1, F2, etc. to F3 be the coefficient of frictions. Coefficient of frictions of pipes 1, 2, 3, 4 and 5. And let H, capital H be the difference of water level in two tanks. Okay. So this difference in water level is taken as H. Now we know the continuity equation for discharge. So the discharge passing through each pipe will be equal to the discharge. We know the continuity equation A1 V1, that will be equal to A2 V2 will be equal to A3 V3, etc. So the difference in liquid levels is equal to, see why this difference in water levels. So the difference in liquid surface levels is equal to the sum of the total head loss in the pipes. So this head is equal to the head loss in pipes. So the head loss in pipe is expressed as H is equal to the major energy losses plus minor energy losses. So you can see here the pipe has a sudden enlargement, sudden contraction, enlargement, contraction. We have entrances of pipes and exits of pipes. So all these are responsible for minor energy losses. So major energy losses can be, we can use the Darcy-Weisbach formula, that is 4 F1 L1 V1 square by 2G D1 plus 4 F2 L2 V2 square by 2G D2 up to V5, right? Up to 5. So 4 F5 L5 V5 square by 2G D5 plus we have minor energy losses. Okay, and if these minor energy losses are neglected, we have the major energy losses as H is equal to 4 F1 L1 V1 square by 2G D1 plus 4 F2 L2 V2 square by 2G D2 plus etc. to up to the fifth pipe. So 4 F5 L5 V5 square by 2G D5. And if the coefficient of a friction is the same for all the pipes, we have the head loss will be equal to 4F by 2G into L1 V1 square by D1 plus L2 V2 square by D2 plus L3 V3 square by D3 plus L4 V4 square by D4 plus L5 V5 square by D5. Okay, this is how we have to calculate the energy losses when a pipe is connected in series. Now, we will see what is an equivalent pipe. Equivalent pipe. Okay, so what is equivalent pipe? It is defined as the pipe of uniform diameter. See, when we have a series of pipe with different diameters, equivalent pipe is a pipe of uniform diameter having the loss of head and discharge equal to the loss of head and discharge of a compound pipe consisting of several pipes of different lengths and diameters. So the uniform diameter of the equivalent pipe is called the equivalent size of the pipe. And the length of the equivalent pipe is equal to the sum of the length of the compound pipe consisting of different pipes. Okay, so our length L will be equal to, so I think there is no need, okay. So when we have a number of series of pipe, see, we will take, for example, we will consider 3 pipes connected in series. Okay. So 1, 2 and 3. So 3 pipes are connected in series. So we have L1, L2 and L3 with the length of the pipes 1, 2 and 3. D1, D2 and D3 with the diameter of the pipes 1, 2 and 3. Capital H is the total head loss. Now, L be the length of equivalent pipe. Okay, L be the length of equivalent pipe and D be the diameter of equivalent pipe. So, our aim is to replace this pipe or compound pipe with the help of a equivalent pipe so that the losses will be equal. Okay, the loss of head and the discharge through this equivalent pipe will be equal to the loss and discharge through this compound pipe. This is called compound pipe. That is, more than one pipe is connected. This is called equivalent pipe. Equivalent pipe for this compound pipe, equivalent to this compound pipe. So, equivalent pipe means it should have the length and diameter which will have the loss of head and discharge equal to the loss of head and discharge of compound pipe. Okay. So, what is called equivalent pipe? Equivalent pipe of length and diameter having the loss of head and discharge which will be equal to the loss of head and discharge of the compound pipe. That is called equivalent pipe. So, see, we know the total head loss. Major head losses, we have 3 compound pipes. So, that will be equal to 4F1 L1 V1 square by 2G D1 plus 4F2 L2 V2 square by 2G D2 plus 4F 3L3V3 square by 2G D3. Let us assume F1 is equal to F2 is equal to F3. And the discharge Q will be equal to A1V1 is equal to A2V2 is equal to A3V3. So this will be equal to pi by 4 D1 square into V1, which is equal to pi by 4 D2 square into V2 equal to pi by 4 D3 square into V3. Also, now we will equate this velocity V1, V2, V3 in terms of Q. So equating we will equate these both and these both. So that we will get V1 is equal to 4Q by pi D1 square. V2 is equal to 4Q by pi D2 square. And V3 is equal to 4Q by pi D3 square. Now we will substitute this V1, V2, V3 in equation number 1, that is in our energy head loss. Okay, so when we equate, we will get 4 into 16FQ square by pi square into 2G multiplied by L1 by D1 raised to 5 plus L2 by D2 raised to 5 plus L3 by D3 raised to 5. Now, see, this is the head loss. This is the head loss for the compound pipe, okay? So, as per definition, this head loss should be equal to head loss of the equivalent pipe. So, this should be equal to 4FLV square by 2GD. So, this is the head loss of equivalent pipe. So, that is equal to H. Okay, so head loss should be equal for both compound pipe and equivalent pipe. Now, for the equivalent pipe, we will take V is equal to Q by A, that is 4Q by pi D square. Substitute A is equal to pi by 4 D square. So, we get H for equivalent pipe. So, this is H for compound pipe, okay? This is H for equivalent pipe. So, H equivalent will be equal to 4 into 16Q square F by pi square into 2G into L by D raised to 5. So, now we will take this as equation number 2 and this as equation number 3. So, equation number 2 is equal to equation number 3, right? Equation number 2 is this is replaced by 4 into 16 Q square F by pi square into 2G into L by D raised to 5. So, this term equating 2 is equal to 3, we get L by D raised to 5 is equal to L1 by D1 raised to 5 plus L2 by D2 raised to 5 plus L3 by D3 raised to 5. So, equating 2 and 3, we get L by D raised to 5 is equal to L1 by D1 raised to 5 plus L2 by D2 raised to 5 plus L3 by D3 raised to 5. So, this is the condition for equivalent pipe. So, L is the length of the equivalent pipe, D is the diameter of the equivalent pipe, L1, L2, L3 are the length of the compound pipes connected in series 1, 2 and 3. D1, D2, D3 are the diameter of the series pipes connected in series. D1 for the first pipe, D2 for the second pipe and D3 for the third pipe. Okay. Now, see, this is the case if it is connected in series. Okay, this is very, very important for solving the problems. So, now, If the pipes are connected in series, we saw the Q will be same, right? Q will be equal to A1 B1. So pipes connected in series. Q will be equal to A1 B1, that will be equal to A2 V2, will be equal to A3 V3, will be equal to A4 B4. So we have 4 pipes here, 1, 2, 3, 4. Now, if the pipes are connected in parallel, what happens? If the pipes are connected in parallel, see, you may have one pipe like this. It can be branched into 2 different pipes. Okay, this pipe can be branched into 2 different pipes. Then it can be branched into another pipe. Okay, so it may move on like this. It may go on like this. So finally, it can be branched into one single. One single pipe. So we have 1, pipe 2, pipe 3, pipe 4, pipe 5 and pipe 6. So if this is the case, what will be the condition? So our continuity equation will be Q1 will be equal to Q2 plus Q3 and Q2 will be equal to Q4, Q3 will be equal to Q5. Now, what about this 2 and 3? So, Q2 plus Q3 will be equal to Q4 plus Q5. And coming here, Q4 plus Q5 will be equal to Q6. Okay? If the pipes are connected in parallel. So, based on that, how will be the losses? Now, we will consider pipe 1, 2 and 3. Okay. So, suppose we have a pipe. This is branching into 2 different pipes. Then it again comes to one pipe, one outlet. So if this is the case, the loss of head in branch pipe 1, this will be taken as 1. If this is taken as 2, the head lost in pipe 1 will be equal to the head lost in pipe 2. Okay. So that means our 4F1L1 V1 square by 2G D1 will be equal to 4F2L2 V2 square by 2G D2. That's all. So with this, our concepts of the third module is over. Now we have problems related to this. So what we have studied today is, first of all, we saw what is losses. We saw what is major losses, what is minor losses. So major losses, we have 2 different formula to determine, that is Darcy-Weisbach formula and the Chessie's formula. So we saw what are the different causes of minor losses and the formulas related to that. Then we saw what is hydraulic gradient line and a total energy line. After that, we saw the equivalent pipe. So the condition is L by D raised to 5 is equal to L1 by D1 raised to 5 plus L2 by D2 raised to 5 plus L3 by D3 raised to 5 plus etc. Then we saw the pipes connected in series and pipes connected in parallel. So these much concepts we have studied. So with this, the concepts of the last modules are over. We have problems related to this. So 3 or 4 classes we will do the problems related to this concept. And with that, our third module will be completed. Thank you.